Pixelview. This is a program I wrote a few years ago to look at graphics data and map data from old games. That was my initial interest. But it's really good at kind of just visually inspecting data files and figuring out what's in them. If anything is an uncompressed grid of data, it tends to be pretty good at finding it and sort of visualizing it in a sensible way. So I'm just going to start with, so I have this armorrab.mon. This came from a shareware DOS game called Espetra, which I just wanted to know what was in that game. So I started looking at the files. And basically the way this tool works, so like the preset I've started with is 8 bits per pixel. It's very plain, so it's just every byte maps to a color in this palette. You have different choices for palette. There's some auto-generated ones, and you can load your own. I'll show you that in a moment. But the basic step is you start by setting the width, and you try and find a width where things start to line up. So like that looks kind of interesting there, but it's not quite right, which means we're probably close to like an integer multiple. So 16.5 maybe is somewhere close. So what's that? 30, 33. But let's keep going. Oh, 24, 25, 25 looks aligned, but there's kind of stripes in it. So we might be getting half of it. So if we just double that, there's 50. But to show you, like going up and down from 50, see how it's like it's very slanted, and when you get close to the right number, it starts to you're shifting by 2 pixels every line here, and now we're shifting by 1 pixel every line because we're off by 1. And when we finally get it, it all just lines up. I should probably increase the zoom here so you can see it. And that's the start of finding the image data. The next thing is maybe you want to pick a starting position. So there's some bytes at the start of the file, so we'll just advance until it looks like we've captured the image. When the height is 1, it'll just sort of stack each row of pixels vertically. But as soon as you have a larger height, it puts a gap between each image. And you can customize the color of the gap if you want. Like we could make this, I don't know, whatever color is convenient. But so to find the height of the image, we can do this. But it looks like there's some data between this part and this part. And I'll sort of explain how to deal with that in a moment, but maybe not with this example. So that shows me the image data. I can hover over a pixel. I'm going to see the value up here. So this has a value of 0. Down here, you can see how this has a value of 255. So this looks like a map. They're all like 0, 255, whereas this has a bunch of different color values. So I made a palette file, which is just like triples of RGB values, like 8 bits for red, 8 bits for green, 8 bits for blue. But there's a couple of different formats here. You could load a PNG image that just has your palette in it if you've got one of those. But here you go. I think this enemy is called Armor Rabbit in the game, and that's what it looks like. That's the image found. And so if you've managed to find the palette somehow, this tool can kind of be used to look for palettes, and that's a bit more of an advanced topic, and I don't really want to cover it right now, but this tool can help find palette data. There's even a pixels to palette thing. Like if you can display the palette as pixels in this view, then you can just right click on it and copy it to the palette, which might be convenient. Often I write like a Python script. Actually, in this case, I did write a Python script to help me extract the palette for this a few minutes ago. But there it is. There's the basic image. But the other thing I said, let's go back to RGB and and then just auto-generate that. So this is Legacy of the Wizard. Maybe I'll zoom out a little bit. This is probably good. So let's go back to height of 1. Again, we're still using 8 bits per pixel. 1 byte is 1 color, 1 pixel. So in this case, so we can already see, if I get to width of 48, it starts to look regular. Like it's not slanted, but the regularity in here seems to be repeated. So this is probably, well, if you see 1, 2, 3, 4 repetitions, probably means that we're like 4 times the value it needs to be. So as we continue down, so you can see as we get to 37, 36, so 37 looks diagonal, and then 36 looks vertical. And again, this kind of looks like a 3 times repetition. So we seem to be like rapidly approaching 12, right? And there you go. So you find 12, all of a sudden everything lines up. And then you can see that there's a repetition, like this kind of area, this like black stuff with like rainbow values. There's a chunk of these at regular spacings. So at this point, maybe we can adjust this until those align. So we make the image height taller and taller and taller. And then eventually we find we can't quite make them line up. So this is where I want to talk about, so this is the packing window, and it just tells you how bytes are packed. So normally the auto button means that you have 8 bits, it'll read a pixel, then it moves on to the next 8 bits. It's all contiguous. That's what auto means. And then after 12 pixels, we move on to the next data in the file. So at this height, so I don't know if it's 85 or 86, but it seems to be somewhere in between, right? But if we stop treating it as an image, but maybe it's like a grid and then there's some extra data. So we could change this value. So we can adjust this until they line up. And so we see that's still kind of diagonal. And there, right there, they all turn into this regular repeating structure, right? And that's it. So it's 124. That makes sense. It's a 1 kilobyte block that repeats. The other thing is we want to kind of align it. So is this where we want? Actually, yeah, that looks good. So that's it. And you'll notice that if you've played Legacy of the Wizard, you might start to recognize details in this room, like this sort of room with like a fish shape in it. That might look familiar. Here's kind of a ship. So some of these rooms might look familiar if you've played the game. Actually, I can zoom out. Or maybe if we zoom out far enough, you can see, hey, there's this whole big block of level data. So when I made the Legacy of the Wizard editor, LOTW tool, a few years ago, this tool was my starting point for how to find the data. Like I look for data like this, and then once I've found it, I start kind of like inspecting the pixels. I open up in a hex editor, I start writing Python scripts or things to visualize it in different ways or just inspect the data. I might try tweaking things and see if they make changes in the game when I play it, that kind of thing. And you figure out how the map data format works, which is pretty cool. Like that's what I made this tool for. But I also mentioned that you can just sort of inspect the data in the file width. So let's use like a generic size. So like 128 by 64. Let's turn auto back on. So the spacing is correct. Usually you want auto when you're messing with these. You turn it off once you've figured out the format and need to adjust and not do something contiguous. But But look at this. So we have, these are clearly regularly spaced. Even though the color's changing, there is a structure that you can see. And then we get here and all of a sudden something changes. Like this is clearly different data. This data is all red and green for some reason, so it probably belongs together. Areas like this that looks just kind of like random noise, they often mean there's compressed data, or it could be code. Code often looks pretty random. So you can tell a lot of things about where, not necessarily what the data is, but you'll know that there is some data with regularity here, a different kind of data here, a different kind of data here. This one has like really interesting regularity. And actually, let's go to the end of the file now. And then if you know about NES ROMs, you know that the files, or there are often like two ROMs in an NES cartridge. One side is code and data, the other side is all graphics tiles, and graphics tiles are in a standard hardware format, and that's what these presets are for. So I have this preset menu, and in this case, NESCHR 8 pixels, and here we go. It's all, you can already see like the graphics. So that's it. Like here are here's the graphics data from the game, and you can visualize it. Let's do the Cube Helix palette. That's kind of nicer to look at for the moment. Often this is helpful for finding font data. But maybe I should explain, like, so how does a preset come together? So the definition of how to read a pixel, like the preset, basically all went into this packing window. And I can show you what everything means. So hang on, I'll focus myself on the start of a font set, I guess. Position to pixel, I can right click on this and, oh wait, it's already, that's the start of the window. Sorry, let me do that again. So if I move this, if there's like a pixel in the middle and I kind of want to start there, I can right click on that pixel, then just click position to pixel, and there we go. But actually what I wanted to show is that if you use a horizontal layout, sometimes that's better. I start with vertical because that's usually better for visualizing continuous data in rows. But sometimes you want, once you've found it, there's a regularity in collections of images, and you kind of want to lay them out horizontally. There's another option I added recently, was this pixel window. So normally the only way we had to resize or to choose how many are in a column was to resize the window, but that was inconvenient because the window was also the control panel. That option lets you separate the control panel. So there's 10, 11, 12, 13, 14, 15, 16, and 16 is often a natural organization point for NES stuff. And I think I need, I lost my starting point, but we can go back to, oops. There we go. Oh, it's a little bit off, but I can use this to, actually I think it was there. Anyway, that's sort of how to find the data, but let's say we didn't know the format. So we're at this region of pixels. I'll make this half the size, but so let's say we started at, this is kind of what a default looks like, and you would have auto for all these. So this doesn't look like pixels, does it? Or it doesn't look like recognizable graphics. Often what I do is I start at 1 bit per pixel, and here we can see like there's recognizable stuff here, and it looks like we can see the font characters. So if we had guessed 8 bits, or sorry, 8 by 8 tiles, 1 bit per pixel, Often 1 bits per pixel. Like if it's really 2 bits per pixel, you might see 2 copies of everything. Maybe horizontally it'll be twice as wide, or it manifests in different ways. But in this case, we see 2 copies of everything, so the 2 4s, 2 5s. That's a hint. They're backwards, so we can click reverse byte. So there we go. In this case, so if you know about the NES, you can look up its standard graphics hardware format. But sometimes you got to try things to figure things out, and you can get you can learn a lot about trying to put these formats together. I've looked at a lot of different games now, and sort of figured out ways to figure out graphics data when it's like a software format, and I don't know. But if it's something like the NES, oftentimes you look to documentation of the hardware, if you can find it, that tells you these things. So we need 2 bits per pixel because that's what the NES does. But they are not chunky. Chunky means all the bits are contiguous. So you have 2 bits, there would just be 2 adjacent bits in the file. That is not what we have the NES. So it's not chunky. What we need to do is skip 8 bytes ahead. And this is already entered in from the preset, so I already got it there. So normally this would be 0, 1. Like there's a bit, there's the next bit. Contiguous, 1 bit apart. That would be the chunky version. Like that's what that means. But if we go 8 bytes ahead, that's actually where the data is. What happens is there's 64 pixels. You get the first bit of them, and then you have 64 more pixels in another 8 bytes. And that's the second half. So we do that, but now the spacing is wrong. So that's what this auto button is for. So if it's auto, it's contiguous, but this is not contiguous. We need it to go 1 bit at a time. However, after going 64 pixels, we've reached the bottom of the image, and we jump to the next one. It's not right after because there was the second whole plane of bits, another 64 bits. So we need to change this here. So they're actually 16 bytes apart instead of 8 bytes apart. And that's the format. I don't know if that's a confusing explanation, but that's basically how this works. You have some number of bits in your pixel. You have some number of bits which you can arrange in this table in arbitrary orders, arbitrary distances apart, and then you put them together and you get this stuff. Eventually it looks like the images, and then I could save all visible to save everything that I can see to a ping file with a palette. It'll look nice. Here's another map example. This is also from a Spectra, but let's just go back to the 8 bits per pixel way that I usually start. And we'll just play with width again, as I usually do. Oh, so we want to go back to vertical layout. Usually vertical is what I need for kind of starting to look at data. I find it tends to work better. So here we go. So at 67, actually it looks pretty much, it looks like a map, but not quite. And there's a lot of spaces between the pixels. And it's just because we're off by a multiple. But if we keep going here, see how it's getting diagonal and then starting to straighten out. And there we go. There's a map. There you go. And there seems to be some, like, there's a couple bytes of header, 7 bytes of header. But I advanced past that, and now everything's kind of lined up. And the reason there's a black column every second column is that this is not 8 bits per pixel, but it's actually 16 bits per pixel. I'm going to visualize that better. But now our width is, because I've gone from 1 byte per pixel to 2 bytes per pixel, now the width needs to be cut in half. So there we go. We've got our map. I don't know if it's better in reverse or... It's not easy to see in grayscale. So often, like with large bits per pixel for map stuff, it's hard to find a good palette. But we can clearly see the structure of the map this way. I guess I could unchunkify it and, I don't know, change stuff. I could put, I'm not going to mess with it right now, but sometimes your data is 16-bit data and you'll get gaps every second column. That's sort of a telltale sign of that. So speaking of 16-bit stuff, I want to show you something from the Atari ST. So fish.neo, this is a Neochrome image file. The title fish should probably help. So once again, starting from 8 bits per pixel. So we know the Atari ST resolution is 320 by 200. Look at that, 320. We already see a fish. 320 by 200. It's repeating, so we've probably got something wrong, but I'll start breaking this down. So Atari ST has 16 colors, which means 4 bits per pixel, right? So now we only see one fish. We've got 4 bits per pixel. But we get these repeating stripes, which is really interesting. So if you don't know the Atari ST hardware, this kind of format can be difficult to figure out. But if you look up what it is, to get the 4 bits of a pixel, the hardware works in 16-bit words. So instead of working with a byte, it works with 2 bytes, 16 bits. And 16 bits refer to 16 pixels, but then it does that 4 times to build up 4 bits for each of those pixels. So instead of the bits, like the 4 bits that we need coming one after another, they're spaced a word apart, or 2 bytes apart. So that's what this chunky checkbox is for. If you uncheck it, I can now say, instead of it being 1 bit later, 2 bits later, 3 bits later, we go 2 bytes later, 4 bytes later, 6 bytes later. And when we do that, well, it still doesn't look right, but we're getting closer. Because we're no longer dealing with contiguous chunks, we've got to turn off auto here. So we need to go 1 bit at a time to advance for the pixel. But that's still wrong, because on the Atari ST, after we've reached 16 pixels, we've still got 3 more words to skip over. So the blocks of 16 pixels are actually 8 bytes apart. And that's what this tiling window is for. So this is another feature of the preset. So every 16 pixels, we want to jump 8 bytes rather than the auto, which would just be 2 bytes. Right, the auto would be like 16 times 4. 4 bits. That would be the right spacing, but now we set it down to 1, and now it's only going 8 bytes. So we get that. But it still looks wrong because this also needs to be corrected. So at the end of the row, we've gone 4 bits per pixel times 320 pixels. So that's half a byte. So we'd actually be 160 bytes per row. And suddenly that looks pretty close. The other thing is there's a header on the file that's 128 bytes. But that looks almost right, but everything looks reversed. So we just click reverse byte, and there you go. That's the Atari ST format. But once again, like this is a preset, this is a hardware format. We can just click Atari ST 4 bits per pixel, and there it is. Like it's ready to go. So usually when you have a known platform, you can try one of these presets, play around with it, and adjust the width to see what you get. And that can be like a quick way to find a lot of these things. When it's a custom format, there's a bit of work to do figuring it out. But yeah, let's go back to 8 bits per pixel. So one more thing I wanted to show you. Here's a sprite file from a game I really like for the Dreamcast called Elemental Gimmick Gear, EGG egg. It's abbreviated. This one, I didn't really know the hardware format, but I did manage to figure it out with this tool. I had to add a feature to this tool to make it work. I determined that it was 15 bits per pixel color format. However, 1 byte plus 8 bits, or you could say 2 bytes. I actually want things 16 bits apart. So we're just ignoring 1 bit, and that bit might be transparency or something. We can't really visualize that well with the tool, but when I did this, I got colors that looked a lot like colors that you'd see in the game. Like these started to look kind of interesting, good colors. So, and I can already see like a repetition of, let's see, there's like green and gray. And I think I found at like a width of like 32, things started to line up. I guess you can't see it that well here. I forget my process, but eventually I arrived at like 32 by 32, and things started to look sort of right, but not quite. And what I realized was that some hardware formats for textures, especially in like more modern systems, to increase caching so that like pixels that are near each other are closer in memory rather than like line by line, where each line, the next line can be far away and there's the whole side of a line that's off screen or you can't see, would be the next bytes, but really you want bytes that are close to be nearby. So that we have these twiddle formats. And these are common in modern texture formats, and the Dreamcast had such a hardware feature. So I believe it was Twiddle M, and to save time, I know where like a starting offset is for this file, but let's just zoom in so you can see that a little better. Here, because it's twiddled, things kind of slide around weirdly. So this is called Morton order or Z order, or there's a bunch of ways to describe this, but and unfortunately, like every second byte, because it's like a 2 bytes per pixel, every second byte's going to be half the wrong color. But I just kept advancing forward and back, and after a lot of trying, I found all of a sudden this. All of a sudden I have like all the sprites for that character in view. Oh, look how it animates when I scroll. That's nice. So that's what that feature is for, but that's sort of an advanced feature. Like these aren't that common unless you're, well, looking at specific kinds of hardware. I mean, if you're looking at like a modern tech, like for a modern game, a texture file, you might have to deal with twiddling. If it's not compressed, if it's compressed, you probably have to uncompress it, in which case you might know the format already. Anyway, this is one of the characters from Elemental Gimmick Gear. which is another game I made maps for, and I just wanted to know everything that was in that game after playing it. I really loved that game, and this tool helped me do that. Anyway, I think that's about all I should say about Pixel View for now. If you want to use this tool, it's open source and free. Please just go download it. Try it out. All right. Thanks for listening.